So let me just recall quickly how we proved that. So we have these polynomials that are the time-lapsed divergence of two points that are highly typical, very nicely equidistributing, etc. And then we choose a subsequence of such time-lapse polynomials to find a limit polynomial. And the game is that the measure is invariant under the limit polynomial. How did we prove that? First of all, to check invariance of the measure, it suffices to look at how you integrate continuous functions before pushing it by the value p of tau and after pushing it by the value p of tau. Right? Continuous measures are functionals on continuous functions. So if you know how the continuous functions behave, you can prove this. Now, the second step was that we had two orbits that really defined the sequence of polynomials. Two sequences of orbits, actually. And let's say we have the blue one, which I don't draw too complicated because it's too messy to do it. And then we had another one, don't know whether the colors are correct, and the 2 points are very close together, and it takes them a long time to move away from each other, but we actually go as long as is needed, and then stop. So that we see that they have moved away from each other some amount, but not too much. That was the meaning of the parameter Tn. That's the time lapse that we use. So this is a very, very long orbit, and this is a very, very long orbit, and they both equidistribute in the space. If they equidistribute in the space, and we also know that the first half of the orbit equidistributes in the space, then obviously the second half also has to equidistribute in the space, because it's a convex combination of the first half and the whole thing. Both equidistribute, so the second half equidistributes. I use the same argument not for the second half, but for the last percent. As long as the percent doesn't go to zero, it will go to zero at some point, but not in that stage of the argument. As long as this last percent doesn't go to zero, it remains 1%. This last percent equidistributes in the space. And so does the red last percent. It also equidistributes in the space. But this difference, this displacement, is almost that value. And we check the statement for a continuous function, so we use uniform continuity of this continuous function of compact support, and we realize that statement. Now, of course, you have to do all the epsilons in the right order, but that's the argument. Any questions?
Where did you use the fact, or did you use the fact that the set K of uniformly generic points is almost all the space?
No, didn't use it.
So you just needed the sequence.
I started assuming, let's suppose I have 2 points, a whole sequence of tuples of points that are uniformly generic. How to find them I didn't tell you yet. So that's where we will use that we can really have large sets of uniformly generic points. It's an if-then statement, and it's not yet clear how to get the if. Okay? Now, let's start the proof of this semi-simple case that we stated before. We have SL2R acting on X G mod gamma. SL2R is in a particular way a subgroup of G, and mu is invariant and ergodic, which implies mu is invariant and ergodic under U 1 T1, and that means we have a large set that exists a set K of uniformly generic points of measure bigger than 1 minus epsilon. And now I need to bring into the picture the stabilizer. Somehow we want to show that the measure is supported on a single orbit of the stabilizer. So let us define L as the connected component of the stabilizer. I don't know the stabilizer, but I know the stabilizer closed subgroup of the group G. Closed subgroups have connected components, and connected Lie groups, connected subgroups have nice Lie algebras. So let's say Lie L is the Lie algebra of L sitting inside the Lie algebra of G. We don't know it, it's determined by the measure. Obviously, our SL2R, the way it acts, it's a subgroup of G, preserves the measure, so this SL2R is sitting inside L. So obviously, Lie L is invariant under SL2R with respect to the adjoint action, which just is the derived conjugation action. If we have an invariant subspace in a finite dimensional space for this nice group, then there exists an invariant complement. There exists the set, which is an invariant complement. There's no claim of uniqueness, it doesn't matter. Where the invariance is with respect to SL2R. Possibly not invariant under all of L. Maybe L contains lots of unipotents, and unipotents don't have that statement that they are invariant complements. But it's invariant under SL2R. Okay? Now, let y equals xg, g goes to the identity, and typical, whatever that means. I will fix that in a minute. If this assumption, y and x are typical, whatever it means, and the displacement is close to the identity, if this implies G is in L, maybe it does, because we don't know the measure. If this is what this assumption here implies, then the L orbit there is an L orbit that has measure 1. But L preserves the measure, and we are supported on a single L orbit, so it's done. That's the thing that we want to show. If not, we have to show that L was chosen incorrectly. We have to show that there is actually a bigger one parameter subgroup outside of L that still preserves the measure. So we want to show that we are always in this case. That's what we want to show. Now, let me erase all of that and define the set that we really use. Let me define it here. X1 is the set of all x in X, such that I'm taking the one ball in the group L with respect to some metric that we've chosen around the identity, and I'm integrating over this one ball f of x L, L inverse of S, one of the two, dm L L. And I want this average to be bigger than 0.99. Now it looks like an ergodic theorem, right? I'm averaging over a piece of the orbit. So it looks like I should be saying something about immutability of L or whatever. But no, I don't say anything about that because I'm not going to infinity. This is my radius, 1. 1 doesn't go to infinity, it's 1. And this is my group in which I say inside I take the ball, and this is what I average. There's nothing going to infinity, so there's no ergodic theorem used in the definition of this.
Who is F? What is that?
What is what?
F.
F is, thank you, characteristic function of K. F doesn't make sense. What is K? K is a uniformly generic set of points. A set of uniformly generic points. And the only thing I know and need is that the measure is preserved. The measure that I'm looking at, the measure mu, which I don't understand, don't know, is preserved by this group L. Which implies, just by Fubini and some easy inequality, that the measure of x1 is bigger than 1 minus 100 epsilon. Just a silly inequality again. Apply to the complement of the set.
What is epsilon?
Epsilon is epsilon. Maybe I need it, maybe I don't. Suppose x is in the support of mu restricted to x1. I have a probability measure, I have a set of measure 1 minus 100 epsilon, big measure, and I restrict my probability measure to the set of big measure, I get some measure which has some support. If my x is in the support and y is very close to x and y is also in x1, and say it's also in x1, take 2 points. The 2 points differ by very little, and both points are in x1, and to ensure that I can choose the second point close by with this property, I just take my first point within the support of the measure restricted to x1. That statement just means there are lots of points with that assumption.
Something is fishy here because only very close by to x you can find points y which are in the support of mu. But it's in the support of mu restricted to x1.
Yes.
Okay.
This restricted here is very important for what I'm doing, and measures have support as long as they are not a zero measure, right? This is not a zero measure because epsilon is small, of course. Now, I take an x that is in the support of the measure restricted to the set, which means I find lots of points other than x, because the single point is measure 0. Lots of points that are close by and also in the set. Now there could be two scenarios. This is what I started doing here a bit informally. There are two possible scenarios. Maybe this statement here implies that the displacement is in L. Let me put this in a different color. So this is
the end of your definition of typical?
This is now my definition of typical. It's not really typical, but so if this implies y and g in L, then we get from this part here that mu of xl has positive measure. Right? Because there are lots, there is a positive proportion of points near x that are still in x1. That's what this is saying. There's a positive proportion of points near x that are still in x1. If all of those points are actually in the L orbit of x, then the L orbit of x has positive measure. If it has positive measure, it has measure 1. And since L preserves the measure that I'm looking at, I'm done. So now we need to work with the assumption this is not true. G is not in L. So xn equals x, yn equals x gn, gn going to the identity, gn not in L. That's what we have currently. You can choose a sequence of points in x1 and so on. Now, suppose we start the procedure. We start the polynomial shear lemma for these points. Then we will conjugate ut gn, ut inverse. We will conjugate the gn by the tn, by the t, and start to see stuff. And then we have a limit polynomial p of tau after the speeding up and choosing a subsequence so that the sequence of polynomial converges, we get something. And that takes values in G. Maybe in L. Then it's useless, we don't get a contradiction. And this is where our invariant complement comes into the picture. If we can find xn prime yn prime equals xn prime gn prime with log gn prime in Z, then we're in business. Because when we conjugate now the log gn prime with the unipotent, the log pn tau is somehow the log of the conjugated elements speeded up, tau tn gn prime u tau n t tau tn inverse. But the conjugation I can also pull out, right? and just write it as the adjoint action of u tau Tn applied to log Gn prime. And this is in Z, and this is in SL2R, which leaves Z invariant. So this takes on values in Z. But if the sequence takes on values after taking the logarithm in Z, then the limit after taking the logarithm takes on values in Z. So we get from, if we can find, that's another if. If we can find these 2 points with the difference in the invariant complement, then the P of tau satisfies log P of tau in Z for small tau. Why for small tau? Because logarithm is defined locally. But that's a contradiction, because the polynomial preserves the measure, and Z was supposed to be the invariant complement of the connected component of the stabilizer of the measure. But this is a one parameter something that lives inside the stabilizer. So it goes, but then by that statement it goes out of the stabilizer, out of the connected component. That's a contradiction. We have increased the stabilizer, we have increased the connected component of the stabilizer. So it boils down to this here. Can we make that possible?
So the only thing where we have, I mean, we only need here that U actually, I mean, that this Z is a U invariant complement.
Yeah,
so
that's the only thing we need, but for unipotents you never have such invariant complements. That's why I need the SO2. And now I use a density argument and play around with smooth functions and say it's always possible. If you have this here, then define x n prime by x n Lx inverse, say, and y n prime by yn Ly inverse, where I want my Lx and my Ly to be in the one ball. And then I realize that the new displacement would be Lx G n Ly inverse. And I take the logarithm of that and decompose it into the component in L and the component in Z. And this here is a smooth map from Lx Ly to Li L direct sum Z. Right? The Gn is very close to the identity. If I take Ly equal to the identity and G equal to the identity, then this smooth map in the parameter Lx is just a logarithm map and takes on values in Li of L. And of course the derivative of that map is basically the identity in this special case. So, and the same would go for Ly, maybe then it's minus the identity. So it has full rank for the implicit value theorem. I'm just using nothing, analysis 2, something like that. And I want to set this part equal to 0 and use the implicit function theorem to solve for Ly as a function of Lx. Find Ly equals smooth of Lx such that log Lx Gn Ly inverse is in Z. So now I have one free parameter left. I had two parameters. Now I use the implicit value theorem to, implicit function theorem, to solve for one of them, and I have one variable left. And this smooth function is in C1 very close to the identity. By choosing the Gn close to the identity, this is very close to the identity. In the C1 topology, which means its Jacobian is very close to 1. It's almost measure preserving. And it's almost mapping the one ball to the one ball. So I have almost a measure preserving map from the one ball to the one ball. And I want, of course, two things at once. I want that the xn prime is in K, and I want that the yn prime is in K. I need that. If I don't have that, I would be in trouble. Because that's my assumption in the polynomial shear proposition. But this function is almost measure preserving, and 99% of the Lx satisfy that the image point is in K. And 99% of the Ly's satisfy that the image point is in K. And it's almost measure preserving, so 90% of the values of Lx will have the property that the xn prime as defined is in K, and the yn prime is as defined using this implicit value function, and this, that it's also in K, but then the Gn prime is in the orthogonal complement. Quotation mark, orthogonal complement. And now I should say one more thing. Either the Gn prime that we now found is in the centralizer. Could be. That the Gn prime is now in the centralizer of our flow. Well, then we apply the lemma instead of the proposition. Because the Gn prime will be also as very small. The Gn is very small, it's going to the identity. The Gn prime is also going to the identity. It comes out of the smooth function business. So, if the Gn prime is now in the centralizer, we apply the lemma and get the same contradiction. Because if we find very close, lots of elements in the orthogonal complement that preserve my measure, in the orthogonal complement of the connected component of the stabilizer, of the measure, that's a contradiction. And if we are not in the centralizer, then we apply the proposition along some subsequence, and we obtain a one-parameter family in the orthogonal complement of the connected component of the stabilizer that preserves the measure, again a contradiction. So we must always be in this scenario, which means we get in this scenario, which means we are done. Any questions? So many. It's in the notes. Now there's less information on the blackboard. Is there now a question? Whiteboard. Okay. So you have to fight a bit with the incoming displacement in this proof to make sure that the divergence that you get, the limit polynomial that you get, is not old stuff. You need to make sure somehow that it's new stuff. And here we use the invariant complement and just this smooth argument and almost measurable preserving argument, Jacobian is almost equal to 1, etc. Use this to ensure that we get new invariants from the argument. Let me give you let me tell you that this is not always possible with this proposition. So going back to the horocycle flow, let's try to use the proposition for the horocycle flow. Y equals xg, both generic, maybe along a sequence, then we have gn, and we conjugate the gn, right? We get 1 s t 1 1 minus t 1, and the gn is an, let me drop the n because it gets too annoying. The gn is an ABCD matrix like always, so we have a C here that's very easy to calculate, then we have an A maybe plus TC, and then we have here D minus TC, and that's the most complicated corner to calculate. Here we have some quadratic. And let me just tell you what's happening when you apply the proposition to this sequence of polynomials. You have to speed it up. The speeding up parameter is definitely related to C, and the quadratic also uses the expression D minus A, so you may have to choose the correct speeding up parameter depending on C and D minus A. And if you have done that correctly, then it will converge to 0, 1, 1 polynomial. And this polynomial is either linear or quadratic. No other possibilities, and you will conclude from the proposition that your measure is invariant of the horocycle flow. Not very useful because that's what you started with from the beginning. Now, there's a way to fix that. And the way to fix that is to completely rewrite the proposition. Now, let me explain what you want to do. Again, in the picture. So what happens is the following. You have the 2 points, x and y, that we always looked at, and the 2 orbits. And the second orbit has the property that it moves away from the other one, all right, but it moves away from the other one in the direction of the flow. So the second one is a bit shorter than the other one, and you would use this to get invariance in the direction of the flow that you're working. That's stupid. So you shouldn't use the same time window for the 2 points. If you use different time windows, you just let this one keep going, and then keep going even further, and always use different time parameters for the 1 point and the other point, you can make sure that you diverge in another direction other than the direction that you already understand. So you wait longer and then get a divergence that is different. Now, the thing that you have to calculate to do that is precisely this matrix product. Because you, if I get it right, I take, let's drop the n's because they're too annoying to write all the time. And the G is an ABCD, and then I replace my this time I want the -1 there, then it matches what I have there. So replacing the x by u sx inverse and the y by y u s y inverse, replaces g by this expression. If you figure it out, it becomes really u sy g u s x inverse. Hopefully. If it's not correct, then you have to play with the minuses a bit or switch sides or something. But I think it's correct. So it's the same calculation as before, except that I use different times on the left and on the right. And here's the quadratic. If sy is equal to sx equal to s, then this is a quadratic term, which seems to be more important than the linear term that we have here. That was the old discussion. But now we do the following. We take this expression and set it equal to 0. And use this as our definition of sy in terms of sx. So
you intentionally excluded the b?
yeah, the formula gets simpler this way, why not? B goes to 0 later anyway, so who cares about it? So define sy as asx divided by d minus csx. Now there are two possibilities. C is equal to 0. That's sort of a special case in this discussion. And then you prove the following lemma, which is a complete analog of the previous lemma. Namely, if x equals yg, and g is not in the centralizer but is in the normalizer of u, and both x and y are generic, then g preserves mu. And it's the same picture as before, except that you use different time windows for the 2 points. Because the g is maybe mapping your orbit to a slightly longer orbit or a slightly shorter orbit for the other point. But it maps the equidistributing orbit to the other equidistributing orbit. And that's the only thing needed, and that gives you that g preserves the measure. And that corresponds to the case where c is equal to 0. Your g in SL2R preserves the whole cycle flow if and only if c is equal to 0. So we assume, as in the previous discussion, c not equal to 0, and have now this real rational function. So you might say rational, that's very complicated because there are poles, right? But let's just agree that we use our time windows in such a way that we stay away from the pole. If we make that assumption, then there's no difference between a sequence of rational functions of that form to the sequence of polynomials that we considered before. If you have now a sequence of such rational functions, you have here dn, cn, an, and the ad goes to 1 and c goes to 0 because the g goes to the identity, then this would stabilize to the identity map, right? But if you use that time, then the c, if you don't speed up, you need to use time lapse again, Zeitraffer. You need to do time lapse. A speeding up parameter, you need to introduce that. If you would not do that, then obviously this just goes to the identity again, which you don't want. So you introduce a parameter Tn equals 1 over Cn and use this as your speeding up. And then you have a parameter tau y, that's the speeded up one, is equal to an s tau x dn minus, and this you need to divide this equation by Cn. And then you get here tau y and here tau x. But this tau x, this Sx is not being divided by Cn if you divide the whole equation. But there's a Cn anyway. So that if you introduce your, what's the relationship between the old one and the new one? Now I multiply this equation with Cn, and the relationship is precisely that tau x is equal to Cn Sx. Cn is small, Sx goes a long time, but my renormalized variable, it doesn't go a long time, it goes from 0 to 1. So this is the formula, which means I multiply this equation with Cn. Here I see the tau y, here I see the tau x, and here I already have the tau x. Yeah, the tau y has the same formula. So that's my algebra that I do. And then I do the proof of the proposition again.
Then you use the finite dimensionality of the space of polynomials.
I just use, yeah, there I used it. But here it's a very concrete sequence of rational functions where the numerator is a linear thing, and very easy, and I know that everything converges very nicely. I know that because I stare at the formula. And if you worry about more general things, let's worry it at another time. But that's the procedure to follow now. Good. So what do you inherit after you've done all of that? In the limit, mu is invariant under many values of the rational function what's the rational function? In the limit, it's c is 0 in the limit. The Sx multiplied by c here becomes our variable tau x. And d is in the limit 1, so we get 1 minus Csx is tau x. And then the determinant always has been 1, so it always is also 1 in the limit, so we have here 1 over 1 minus tau x. And then the upper corner we brute force set equal to 0, so that's the limit thing that we are invariant under. And the argument works because the sequence, the renormalized sequence after doing the time lapse, this sequence here converges uniformly on compact sets away from the pole to this one. So what does many values mean? You get invariance of all the values up to the pole but not past it, because you can't go there with the argument. But it doesn't matter because you get already lots of elements from the geodesic flow that you're invariant under. We also skipped one other trivial case. What is happening if maybe the c is equal to 0 all the time, and even more than that, a is equal to 1 and d is equal to 1 all the time? Then we really can't do anything, and we only have elements in the orbit direction. But if the only elements that we see close by to a nice typical point are again points from the orbit direction, then this orbit has positive measure, hence we are looking at the closed orbit, the periodic orbit for the holocycle flow. Those we always have. But if we have other points, then we always end up in this case that we are invariant under elements of the geodesic flow. So either we are, so let me give you the theorem that is being proven by this argument. And it's actually slightly different from the previous theorem that we talked about yesterday. And it should be, it's a theorem of Ratner, because with this slightly weaker assumption you can't apply the old technique. Let gamma in G be discrete. Let x be G mod gamma and mu be a horocycle invariant and ergodic probability measure. Then, just as before, mu is equal to a periodic orbit measure, or gamma is a lattice, and mu is equal to the normalized H measure. Previously, gamma as a lattice was an assumption, now it's a conclusion, or part of the conclusion. That's the strengthening that you can obtain using this argument as a start.
G is SL2?
G is SL2, yes. Both.
What is the assumption of this statement? Assumption is that...
Of this theorem,
Yeah,
we have a discrete subgroup. We look at the quotient.
okay.
We have a horocycle invariant ergodic probability measure.
Okay.
And then the conclusion is as before. Either it's a periodic orbit measure or it's the H measure. But when I say it's the H measure, I need to say in addition that gamma is a lattice, because otherwise we haven't talked about what it means to have the H measure on X. And it wouldn't be finite volume. It's not a lattice. So that's what I said, that the lattice part is here part of the conclusion instead of the assumption, hence it's a better theorem. And the proof is starting in the way we discussed. Either 1, by which I mean this one, or mu is also invariant under elements of the geodesic flow. And now you could ask, can I use some argument like this again? And the answer is no. Because we have now invariance under the geodesic flow. If we want to ensure that in the next application of the argument we get somehow new invariance, we will have to use the geodesic flow as part of our ergodic theorem, as part of our definition of generic points and so on. But geodesic means exponential, and the speeding up exponentials you shouldn't do, because that doesn't stay nice, right? If an exponential looks like this, and if you speed it up, it looks like this. So it's not helpful in any kind of limit construction. So what you need to do is, the next step is entropy. The second step you use entropy for the geodesic flow. And the still unknown measure mu. So you have some quantity let me write little a for some non-trivial element of the geodesic flow. You have some nice number associated to the measure and the geodesic flow, this element of the geodesic flow. some alpha on the diagonal. Now, entropy for the geodesic flow is always determined by the behavior of the measure along the horocyclic subgroup. And we actually started with the measure as being invariant and ergodic under the horocyclic subgroup. That should tell us, and that does tell us, what the entropy is. It's equal to log alpha squared absolute value, because alpha squared is the speed at which this one corner gets expanded or contracted. Proving that under this assumption requires some amount of work, but yeah, can be done. And there is some extra step. If you do this correctly, if you do this proof correctly, you get some extra information. Let me write this down. This equality holds precisely when mu is invariant under the flow that we are talking about. So that there are many nice statements of that vague form, that entropy for the geodesic flow is determined by the behavior of the measure along the horocycle. One strong version of that statement is you have equality in this formula precisely when you are invariant under the horocycle flow. In general, for a general invariant measure, you would have only an inequality, and somehow achieving the maximal value happens in only this special case. And then there's another then there's a trivial step, namely entropy of the geodesic flow is equal to the entropy of the inverse of the geodesic flow. It's a general fact. If you have an invertible system, entropy for T is equal to the entropy of T inverse. Completely trivial to prove. And now we apply that statement over here. That this equality case happens precisely when you're invariant, we apply here. But it tells us now that we are invariant on the opposite unipotent group, because flipping the sign here flips the two sides. So we conclude invariance of mu under, and we are done. But of course it's a black box. I pulled out the black box, and this black box takes about 100 pages or something. You prove other things along the way in this 100 pages. You don't prove it just in this case. You prove it in a general context. But it doesn't simplify that much in this special case.
So in this black box, somewhere you have to use that you are not on a periodic orbit.
That's already here.
Yeah.
If you're invariant on a geodesic flow, you can't be on a periodic orbit.
Okay.
Let me give you there are a couple of ingredients in this equivalency, in this statement. The most technical, there are two technical steps, two technical parts of this proof. Number one is you need to construct a nice generator. Alex talked about this thing that you can define the entropy in terms of factors to a symbolic space. And these factors you define by a partition. And the entropy is defined in terms of supremum over all partitions. But you can find generators which are partitions that really capture the supremum over the entropies in one go, in one by one partition. And you can construct such partitions in general, but you can also construct it here, and if you construct it here, you get additional nice properties for this generator that you have constructed. And you need to do that to sort of make that link happening nicely. And that takes a long time. And then you need to talk about conditional measures. Maybe Elon will talk a bit about why they enter and how they enter in the afternoon. And these conditional measures you need to amplify to leafwise measures. That is sort of a second class of conditional things. And that's the gadget that allows you to describe the measure mu along a subgroup action, which is a bit boring to do for the horocycle flow. Yeah, you can define these leafwise measures that are measures sitting on the horocycle group. And actually this leafwise measure is the H measure precisely when your measure was invariant from the start by the subgroup that you are acting with. But you also apply it for the opposite where you don't know it yet. And then you might see, before you have done all of that, you might see some weird measures on this opposite group. And you match somehow the behavior of this weird measure on the opposite group to the entropy for the geodesic flow. Okay? And then there's a completely trivial last ingredient, which again brings us back to analysis 2. You have to use strict convexity of the log map, or maybe some x log x map. And let me just do that in the remaining 5 minutes. We started late, so I have still 5 more minutes. And of course it's a complete trivialization of these 100 pages, but at the end of these 100 pages there are 2 pages where you use strict convexity of the logarithm map. And let me give you a completely different dynamical system and show you this step, skipping the 100 pages in between. So let's talk about maybe the times 2 map, or on the torus, or just the shift map on the symbolic space 0, 1 to the set. And then we can take an invariant measure mu, sigma invariant measure on, let's use this one on x, and sigma is the shift map. And then we defined the entropy for the shift map. Maybe my notation is slightly off from Alex's discussion, but this is the dynamical entropy of my shift map. We defined it in terms of for primum over all partitions, but for this particular system, it's one of the easier first steps where you show that the partition P, which is the partition into cylinder set 0 and cylinder set 1, is actually the only partition you have to look at. If you understand the entropy for this partition, you understand the entropy. All the other partitions would have at most the entropy of this partition. This is a generator, and constructing this generator in the homogeneous setting, 50 pages or something. No, not really. But with everything around, it's quite a bit of work to construct this partition, which has equally nice properties in the homogeneous setting. But here it's completely trivial. Look at it.
So are you on 0 or natural?
See, why not? That's the definition of the cylinder. In the torus picture, it would be the left interval or the right interval, where I divide by 1/2. Completely trivial partition, and the entropy is the limit or the infimum. Let me write infimum. That's this sub-additivity lemma that appears in the spectral radius formula also. When you have a sub-additive function, a sequence, and you take 1/n of the values of this, then you get that it converges to the infimum. So that's the formula that you have to look at. And let me just write the definition of the entropy of P down. That's minus mu of 0 log of 0 minus mu of 1 log mu of 1. So it's x log x minus 1 minus x log 1 minus x. That's the function. Minus x log x minus 1 minus x log 1 minus x. X being the value of the measure at the position 0. That's a very nice continuous function, differentiable in the interior between 0 and 1. And smooth. Look at the second derivative. You realize that it looks like this. You have 0 at x equal to 0 and 0 at x equal to 1. And there's a unique maximum in the middle. So you prove that this is always less or equal than the value at the middle. And the value at the middle is log 2. And it's equal to log 2 if and only if this is 1/2 and this is 1/2. That's the strict subconvexity, strict convexity of this x log x function. And using the same thing, you show that this expression here is less or equal than log 2 to the n and equal log 2 to the n if and only if each particular element from this position, which has 2 to the n elements, is equal in measure to 1 over 2 to the n. It's an if and only if, and we have an infimum here. So if once we are dropping down in value, then the infimum is already smaller than this entropy is less or equal than log 2. And if it's for one n only less than log 2 to the n, then the infimum is less than log 2. And if it's all the time equal to log 2 along the sequence, then this is always log 2 to the n. Without the n here, this is always log 2 to the n. And then the strict convexity property tells you that each set of these 2 to the n sets is measured 1 over 2 to the n, which tells you what the measure is. Which means that in this picture it would have been the Lebesgue measure. And this is somehow what's happening along pieces of orbits when I go from here to here. But this along pieces of orbits takes some time to explain. I will use the entropy maybe a bit more tomorrow, but maybe I will also try to give you one other argument of Ratner for her little theorem, as it was called earlier. And maybe I can convince you that you don't have to use entropy. You can also do something else. And that's what Marina Ratner did. Marina Ratner didn't use entropy in her papers. And it works. But maybe a bit more conceptual is really using the entropy. And that's the argument by Margulis and Tumanov. So I will try to explain to you both in these two directions. Are there any questions?
If not, let's thank the speaker.